All right, so magnetic flux continued. Magnetic flux continued. Now what I have given you so far is that the flux is defined as A dotted with B, which amounts to A times B times the cosine of the angle theta. And so if this is the area A with a vector A pointing like this, 90 degrees to the surface, and then you have the magnetic field that points in this direction here, then you would have the angle theta being here between them. Now the only problem with this equation is that this works only if you have constant A and constant B. So you can use this for A and B. A and B are constant. But if they vary, that equation doesn't work anymore. So let me give you an example. Suppose you have a surface that, suppose you have a, what surface should we choose? Suppose you have, oh, why not? Let's just draw a random thing. So let's say you have something that curves like this. It's not bad actually. This should do for the purposes here. And let's maybe extend this a little like that. So there it is. All right, so I suppose you have a, this is your surface. Now obviously a vector here is not constant. In fact, what you will have is you're going to have a vector that points here in this direction, and then here it's going to point a little different direction. Here it's going to certainly point in a different direction. Here it's going to point in a different direction, and then so on, and until somewhere here it's going to point like this, and then perhaps here it's just going to be pointing to the right. So a vector changes, right? A vector changes. And on top of it, you might actually have a magnetic field that also changes, so that perhaps at this location here, the magnetic field does something like this. And then here, maybe magnetic field does something like this, and here it points more like that, and here it points more like this. And then here, maybe it does the same thing, and at the bottom, perhaps it just points like that. It's conceivable that magnetic field could do that. And so in that case, you have to modify the equation for the flux. Now you would still have flux of the magnetic field through the surface. There's still magnetic field that pierces this surface, and so there's still a flux through this specific surface, and so then the flux would have to be modified into the following. So what I have is the magnetic field that varies through space. So let's label this as B, and B would be some function that, you know, just some kind of a vector function where it depends on x, y, and z, and it has a certain specific value at every point in space. I would still have B. B has to be in my flux equation, so here's the flux, here's B. But then the the area here can be broken down into the A element, so that this is the A little bit of A that points like this. Here's a little bit of the A that points like this. Here's a little bit of the A that points like this, and I'll put the A everywhere I drew the vector. And of course, if I want to cover the entire surface, then I have to add all of these up. So what I'll have is B at this point here, dotted with the A, is going to give me the flux through this little section. And so I'll actually draw this little section here, or at least I'll give it a shot. So B, this B, dotted with this dA, is going to give me the flux of the magnetic field through that little section, through that little area dA right there. And likewise, same thing will happen here, right? If I dot this magnetic field, oh, let's go to blue. If I dot this magnetic field B with this dA, then I'm going to get the flux through this little section here, dA. And I think you get the picture. We have to keep adding the fluxes through all of these little sections until we have covered the entire surface. I want to cover the entire surface, that all of the little dAs, not just the ones drawn, but all of them, so that you would draw, have another dA, another dA, another dA, another dA, another dA, and so on. Therefore, you'd have to add them up, and that implies an integration. And so you'd integrate over the entire surface, and so maybe we would call this surface S, and therefore this would be the integral over some surface. All right, so the flux of the magnetic field, I'm going to indicate this with that. Note that this is the flux of the magnetic field. Magnetic field flux. And then few weeks ago we did the flux of the electric field, and we labeled it this way. So this was electric field flux. All right, so keep this in mind. I don't think we will actually do too much with it, except for one significant thing, and that is, turns out that if you do integrate the following, if you do actually calculate the flux over any closed surface, gotta be a closed surface, then you will always get 0. This is a Maxwell's equation. What's a closed surface? So a closed surface would be, a sphere is a closed surface. So sphere is a closed surface. A cube is a closed surface. Closed surface, cube. A paraboloid is not a closed surface. So let's see if can I draw a paraboloid? I could try drawing a paraboloid. So here's a paraboloid. Actually not bad. There it is. There's a paraboloid here, and this thing extends, continues on up these directions, but it's just that it's not closed. Like the top here, this top here is not closed. It is open. So this is not a closed surface. This wouldn't do. But cube is a closed surface. Every side is closed off, and sphere is a closed surface. Every patch is closed off. And so if you integrate over any magnetic field over a closed surface, you always end up with 0. This is a Maxwell's equation. And the only things that I'll say about this, so we're not deriving this at all. We're just sort of stating it, and you should be aware of it. So what I'll add about it, what I'll say here is that this equation comes from the fact that there are no magnetic monopoles. You can't have just a south pole that sort of sits there and has the magnetic field pointing towards it. It just doesn't happen. And you can't just have north pole sitting by itself. It doesn't happen. You always have the two south and the north together within a magnet, and then and so the simplest thing you can have is a magnetic dipole where you have both the north and the south pole. And it is because of this, exactly how so, well, but it is because of this that you end up with this magnetic flux equation, where if you integrate over the entire closed surface, you will always get a 0. So maybe I can motivate it a little. Here's a magnet. Here's a north pole, here's a south pole. Let's draw a magnetic field around this thing. And so the magnetic field would point like this from the north to the south. And of course you would still have magnetic field on the inside of this magnet. Just not drawing it. Maybe I should draw it. So you would have magnetic field that points like this, magnetic field here that points like that. Right, and so you'd have the arrows that do this. Maybe we'll do one more here. Here's the magnetic field that does this. And I'll do one more. Here's a magnetic field line that does this. Okay, and then if you were to figure out a flux through some surface, you could do, how about if you did like a little cube here? So that here's your cube, and the cube kind of looks like, it's like this. And you have this thing sitting like that. So what you will find is that you have two lines that go in. So you have, I'm going to put this in, maybe, yeah, let's just do it in blue. So you have two lines that go into this surface here. You have two lines, two magnetic field lines. So let's say two lines go in, and that's going to give you a certain magnetic field that goes, certain magnetic flux that goes in. I'll give you some flux into this this closed surface, this cube. And then on the other side, you're going to have two lines that come out. So these are two lines in, and these are two lines out. And that implies that the flux, whatever is the flux into this side is also the flux out of that side, and therefore the total flux through this whole surface. So the total flux through this whole surface would amount to 0, because this is flux in would be positive and flux out would be negative. And for that reason, you would have total flux through the surface being 0. So this sort of intuitively motivates the idea behind this Maxwell's, this equation here. Now this equation has a name. it's called Gauss's law for magnetic fields. I'm going to get rid of it. I'm going to get rid of this. Let's clean this up a little. And that's not what I wanted. Neither is that. But I guess this will. Here's what I'm going to do. So, 1 second. Okay, there we go. So this is called Gauss's law for magnetic field, or for magnetism. Magnetic fields. And you may recall that a very similar law for electric fields looked a little different. You have a closed surface, you integrate the electric field over some closed surface. That was equal to epsilon Q enclosed over epsilon naught. Right, and this one was called the Gauss's law. Gauss's law for electric fields. Electric fields. Now this might clarify it even a little farther here. Why is it that you end up with 0 here, but not 0 here? You can certainly have a charge, a single charge, that just sort of sits there. There's no problem with an electric monopole, if you will. A single charge can just sort of sit there, and then it generates its field around itself, and you can visualize a surface of a sphere around this thing, and you can calculate the flux through the surface. Now, when it comes to the magnetic, the simplest magnetic thing you can have is north and a south, and these things here, they one pole, if you will, cancels out in a sense the other pole, and so if you do run a surface around this thing now, there's going to be the magnetic flux through the surface is going to have to be 0 because of the north and the south present, versus here in this case you have a single charge, but here you cannot have a single pole, you have both poles, and so you'd have a magnetic field that comes out and goes back in, right? So flux out, flux in, cancels out. Flux out, flux in, it cancels out, and so the magnetic flux through this surface S here that I drew would have to be 0, versus electric flux through this surface here wouldn't have to be 0. So I'm going to write here on the bottom, this little picture implies that the flux of the electric field does not have to be 0, but this picture here on the top implies that the flux of the magnetic field through the closed surface there has to be 0, right? It's not through any surface. This is just through the closed surface S, and this is also through the closed surface S. All right, so anyway, so now you have two Gauss's law, you have two Maxwell's law. One is the Gauss's law for the electric fields, and the other one is the Gauss's law for the magnetic fields.